Today I'm going to talk about downfall, single instruction, multiple data leaks in cutting-edge CPUs. Today I'm going to first talk about the gather instruction. It's an instruction in Intel CPUs, x86 CPUs in general, a little bit history of this kind of microarchitectural data leaks vulnerabilities, and then I'm going to introduce the gather data sampling attack technique, and how we can use this attack technique to steal encryption keys from other users and applications, how we can use this attack to also steal arbitrary data from other applications, and finally, how it impacts security of Intel SGX secure enclaves. And finally, we're going to talk a little bit about mitigation options and conclude the talk. Let's talk about the gather instruction. The gather instruction is this instruction that is introduced about 15 years ago as part of the AVX2 extension to speed up accessing scattered data in memory. And it has various forms, various data types that you can use it in x86 assembly, but you can also use this instruction as part of the Intel intrinsics library when you're writing C code. And this instruction actually used everywhere nowadays. A little Google GitHub search, I figured out that this instruction is used in things like database, cryptography, scientific computing library, and so many different other places. Essentially, any application that is data intensive, they want to do fast data processing, they can benefit from this particular instruction. So what is this instruction about? Imagine I'm a software developer. I'm trying to write an algorithm that performs some data accesses from a scattered memory. I have a lookup table. I have some indexes. And what I would do generally is that I write a for loop, go through each of these indexes, and access the memory based on these indexes. And here in this particular case, I want to only do a computation where these indexes are odd. So for every other index in the memory. I can rewrite this algorithm a lot simpler by using the gather instruction, which the idea is that you provide a vector of index, a vector of mask, and a memory lookup, and then it does this memory access for you, and then you can use another vector instruction to do the final computation. And this looks like something like this when you have the memory, you have a bunch of data that is scattered in the memory, and then the CPU figure out where this memory exists based on that index register, and it's going to bring those values into this vector register. But CPU designers have a lot of choice to make this instruction super fast. For example, when you access this memory from the DRAM, you may access the same data from the same cache line. And the CPU can use, let's say, a buffer inside the CPU core to essentially reuse the same cache line. So for different memory operations, it doesn't have to go fetch the memory again and again. Or it can use the same buffer to also preserve partial execution of the gather instruction. The gather instruction in x86 can access up to 16 different memory pieces. And sometimes some of these may be serviced faster than others. But you may have some interrupts happening in the meantime, and the CPU can just preserve the data, so when that interrupt resumes, it can go gather the rest of the data. And it can also just forward these data pieces to the next instruction and doesn't have to wait for all the data bits to be available. So this buffer can really help with all of that. Essentially, the CPU can allocate a buffer inside the physical register file and speculatively forward data to the next instructions. So this gather operation executes fast. And this looks like something like this. We have these software registers on the right side, the memory, but in reality, there is this hardware register that is not accessible to the software, and the CPU is going to allocate some entries in this hardware register. It's going to eventually bring these data bits and map them to the software. And in the meantime, it can also continue forwarding this data to the next instructions and continue the computation. Wait a minute, shared buffers forwarding data speculatively. What can go wrong with this? This is fast, but we have seen in the past that this can have some vulnerabilities. If you go back to 2018 when Meltdown was introduced, we learned that CPUs can leak data from other users, and you could leak data from the data cache that is shared across different users on the same CPU core. And the mitigation for that was that there were some software mitigation, but ultimately Intel fixed this in hardware with the 9th generation Intel Coffee Lake CPUs. And then later on in 2019, a few researchers, including myself, we looked at the meltdown fix and we realized that this fix is not working properly and we can still leak data because there are other buffers inside the CPU core that they still leak data. And the response to that was Intel issued a microcode fix. The microcode fix enabled the operating system to flush the buffers across context switching. And also, they suggested to disable hyperthreading for some workloads. And ultimately, Intel fixed this vulnerability again in the Ice Lake 10th generation CPUs. There were some glitches how they pushed this mitigation forward. So there were some parts that would still leak data. Some of the Ice Lake CPU didn't have the mitigations enabled properly. And ultimately, by the middle of 2020 to 2020, we knew that this problem is solved, and we don't have these kind of vulnerabilities that enable an attacker to leak arbitrary data anymore. And one thing all these vulnerabilities in the past had in common is that there are these CPU buffers that are shared across users, and it keep data from other users. And when an attacker could access some memory and experience a fault or microcatesis inside the CPU, they could leak data from these buffers. Meltdown was leaking data from the L1 data cache. There was the fallout or microarchitectural store buffer data sampling, leaking data from the store buffer. And there were also other buffers like line fill buffer and load buffer. And that was like a research effort by multiple people, multiple universities, including myself. And people figured out there are all these buffers and you can attack them. Now, today, I'm going to talk about that buffer in that middle, which is the vector register file, and how the gather instruction can leak from this buffer inside the CPU. Gather data sampling. The idea of the gather data sampling is simple. Once I discovered this vulnerability, it's pretty easy to understand and exploit it. Imagine we have a user that is running some vector operation. For example, the user is loading data from the memory to some of the vector registers. And this is a common use case. And then the attacker executes 4 steps to leak this data running on the same CPU core. In the first step of the attacker is going to execute a series of instructions to put the CPU in a speculative execution state. And here in this case, what we are doing is that we execute a bunch of instructions that create a cache miss. And when these cache misses occur, the CPU is going to execute the following instructions in a speculative fashion. Here, the following instruction is the gather instruction that load scatter data from memory. And then we're going to encode the output of this instruction to the cache and scan the cache. And the last 2 steps is very similar to the original meltdown attack, so I'm not going to really expand on that. So let's see how this looks like in practice. So in practice here, there is a sample code that you can also access online, but the idea is that there is one CPU thread that accessing a bunch of string values, and the other CPU thread can leak those string values when we execute this. So after I discovered this particular vulnerability, then I was like, OK, what are the other instructions that could leak to the gather data sampling? And I wrote a simple tool to automatically find what instructions leak to gather data sampling. The idea is that I collect a bunch of memory instructions from the LLVM assembler test case, automatically execute them, and in the same CPU core, I'm going to execute the gather data sampling and record any data leak that I see. The highlight of this experiment was that I realized all SIMD instructions that load data from memory, they all leak. But that includes things like AES-NI and SHA-NI extensions that are designed for cryptography to speed up cryptography. But also there are some other instructions on x86 that are encoded to microcode inside the CPU that use this vector register buffer. And rep move is an instruction that is available in all applications to copy data efficiently. And this instruction also uses the same register file. And there are also some other special instructions to restore the register context when we perform context switches. This is used in the operating system, in hypervisor, or in anywhere that applications want to do context switch. And this instruction also uses the same register file. And essentially, we can use the gather data sampling to leak data from all of these instructions. Another thing that I was interested in is to know how many data bytes I can leak every time I execute this gather operation. So I designed an experiment that this time I'm going to encode the entire 32 bytes of a vector register to the cache and see how many bytes I observe in the cache. And in the sibling CPU thread that runs on the same core, I'm going to populate the SIMD register file with the same data content that I know what it is. The highlight of this experiment on Intel 11 generation core CPUs was that we can leak something between 2 to 22 bytes of contiguous data bytes each time we execute this gather operation. And a lot of these are something between 16 to 21 bytes. And compared to previous microarchitectural data sampling attack, this is a lot more data, because MDS attacks previously could only leak 3 or 4 bytes every time you would access the memory subsystem. But this time, we can leak a lot more data. Another experiment I did is to understand the data pattern when we leak from this register file. So this time, the test program that loads data into the register file is going to load data with different patterns to the register file. And then I'm going to execute a GDS again, but with different word size for 32-bit or 64-bit granular operation that the gather instruction supports. And the other thing we can do here is also every time we do a leak, we permute the output of the gather operation before encoding it to the cache, so we can choose which part of this vector register we want to leak. The highlight of this was that I realized you can leak only 4 or 8 byte chunks of contiguous data. So the way this data is laid out in the register file, it's not going to be contiguously leaked to the gather instruction, but we can leak up to 8 bytes of data contiguously. But we can also use the permute instruction to choose which part of the register we leak. And that's the kind of data pattern we observed, that we can, on the left side, see the 4-byte data words we are leaking. On the right side, we see the 8-byte data words we are leaking. So this time, we are executing the same test, but we are trying to leak different part of the data that we put into the register file. And we can see that when I provide different indexes, we are leaking different words, like EFGH is leaking now, and the next time IJKL is leaking. So it's different part of the register file. And here also in the source code, we see this test program puts this string data into the register file with using other memory operations. All right. So now we have this powerful primitive that we can use it to attack real applications. So far, we showed out how we can use this to steal data from other threads, other programs. And how can we use this to steal encryption keys? So there is this attack I developed in the research paper, but I provided the proof of concept and video on the website. But the idea is that we have a victim that logs into a computer, and it encrypts random data with the off-the-shelf OpenSSL command line tool. And this looks like something like this. We execute OpenSSL. We ask OpenSSL to encrypt with AES 128-bit. And we encrypt some random data, throw it away, and it uses the same key each time. And here, when we do this, the AES algorithm naturally expands this master key to some round keys, because that's how the AES algorithm operates. And the AES-NI, which is the low-level extension in the CPU, has to every time load all these round keys from the memory to the registers to be able to do encryption. And we know one of these round keys is the master key that we want to steal. And this looks like something like this. Imagine this is 128 bit of data that is the master key. It's in the register. And then there are also some other round keys that the AES has generated. We don't necessarily care about them, but they're going to be in the register file anyway. And there are going to be also a lot of garbage data in the register file because we are encrypting random data. So when we execute the gather data sampling attack on this state, when the CPU has this state, one of the observations is that these round keys are going to be repeated with a high frequency because they are being executed again and again. But those random garbage data is not going to be repeated. So here, the attacker executes the GDS attack, leaking 8-byte chunks of the register file each time. And we then keep these chunks that have a high frequency, but also the ones that have a uniform random distribution, because the cryptographic keys generally have a uniform random distribution. And then we combine these 8-byte chunks to create a list of key candidates for the 16-byte AES key candidates. Or if it's an AES 256-bit, we create those chunks for a 32-byte key candidates. And then we brute force those key candidates to recover the AES key. And we can use two things to do the brute force. One is use the plain text ciphertext pair that we have, or alternatively, we can just test these round keys we have recovered against each other and see which one produced the correct master key. So imagine this is the register file, and here we just show this with 2 round keys, but the same applies when we have the 10 round keys in AES 128-bit. And the idea is we leak the first 8-byte chunks because they have a higher chance of being in the register file, higher repetition. Then we do the same thing for the second one, and then we match all this, and we have a list of candidates. And one of these candidates is the correct AES key. And here in this case, we see that there is only 4 candidates. But when we do this for 10 round keys, there's about like 128 candidates that we have to brute force, which is very easy on a personal computer to do this brute force. Here I have a demo that shows this attack in action. Here I log in to this shared computer, and we see that it's running an Intel 11 generation CPU that is not vulnerable to any of the previous meltdown or MDS attacks. Then another user logs in as a victim. And the victim has some scripts to do the AES encryption I mentioned earlier. And we're going to compile the attack code on the attacker side. Here we execute the victim. Victim is doing some encryption. And this is the attacker. This is the key we want to steal on the victim side. On the attacker side, we have some pieces recovered, and then we do the brute force. And this is the stolen key, which is matching the original key. This time, I'm timing it to see how many seconds it takes. And it recovered the stolen key in about 13 seconds. It's matched the original key. And in the last demo, I'm going to show how this also works against AES 256-bit. Obviously, the brute force takes a few minutes, so I fast forward the video. Let's go here. We are doing the brute force. This is the stolen key. It took about 6 minutes. And it's matching the original key from the user side. All right. Well, I hope you enjoyed that 256-bit AES key being stolen. Now, I'm going to talk about how we can potentially use this attack to steal arbitrary data, not just the data that is accessed by another program. So there is this particular feature in CPUs that they like to prefetch data to speed up computations again. And one of the observations I had is that there are two conditions that the CPU prefetches data that is not even accessed by the software. And the first one, I call it out-of-bound prefetch. The idea is that you ask the CPU as a software to only read, let's say, 100 bytes of data, but the CPU is going to prefetch more than 100 bytes to speed up computations potentially. And the other one, I call it no-op prefetch. The idea is that the instruction doesn't even read any data architecturally, but the CPU is going to prefetch data anyway. And there are two affected instructions that have this behavior. One is this mask move instruction in x86, and the idea is that this instruction conditionally loads data from memory to the vector register file. And it turns out this instruction always loads one cache line anyway, even if all the mask bits are unset, which means even if this instruction is not supposed to load anything, it's going to always load one cache line to the physical register file. The other one is the rep move instruction that I mentioned earlier also. And this instruction is supposed to copy some chunks of data based on the R6 register value, and then from the source register to the destination register. And it turns out this instruction always prefetches two cache lines into the physical register file, even if the size is 0, even if we tell this instruction to not copy any data. So based on the second one, the rep move instruction, I identified several gadgets, the memcopy gadgets, that one can find them in other applications and try to exploit them to steal arbitrary data. The idea is that when we write this memcopy or memmove function and we use it in C application, compilers translate this to the rep move underneath. And we also see that in a lot of softwares, we have this property that we copy users' data from an untrusted source to a local buffer, and we do some processing. And naturally, we do some sanity checks to make sure we don't get any traditional software vulnerabilities like buffer overflows, because otherwise that software would be compromised anyway. And the idea is that these gadgets enable an attacker to exploit these non-exploitable software gadgets to leak arbitrary data. So how does these gadgets look like? So the first one I have here is just a regular memcopy copying user data from an untrusted source to a local buffer. And naturally, what we do here is that we check the copy size and the index from the source, because we don't want the user to provide some malicious copy size or index. So this is a correct copy checking. But when we execute this copy is going to prefetch more data than that size to that physical register file, and we can leak it with gather data sampling. The other one is more interesting. In C programming, one thing that is supported is to call the memcopy function with the size of 0. And when we do that, the rep move also has a size of 0, and both of these means there shouldn't be any copy operation. So a C program or a compiler can optimize these sanity checks, that if there is this, if these sanity checks are not met, put this copy size to 0, and this is a safe operation because that memcopy is not going to do anything. But here, actually, an attacker can provide arbitrary address there, even though that memcopy doesn't do anything architecturally, it's going to load arbitrary data to the physical register file. And the last gadget here is a gadget that it's buggy. It's buggy. The software should not generally do that, but sometimes we see that we find these bugs that are not exploitable. The sanity check only is checking the size, is not checking the index, but the attacker can provide the wrong index. And even if it's not exploitable necessarily because the local buffer is never exposed outside, the attacker can use this gadget to load arbitrary data to the register file. Here in this demo, I'm going to show how you can use one of these gadgets to leak data from the kernel memory. So here, the second gadget is a safe operation. I put this into the Linux kernel with the help of a kernel module just for the sake of the demonstration. And then we can use GDS to attack this and leak arbitrary data from the Linux kernel. And here I chose to leak the Linux banner that's embedded into the Linux binary. All right. The last thing I'm going to discuss is how this impacts the security of Intel SGX. So far, I've demonstrated that this attack can steal data from other users. That could happen from other virtual machines, other processes. But there is also this technology that promises extra security on Intel CPUs. Intel SGX is supposed to protect secure enclaves from other users and the operating system. So any untrusted software that runs on your computer, whether it's the hypervisor, whether it's the operating system, is not supposed to access the memory of this secure enclave because it's protected by the CPU. The CPU does extra sanity checks, extra access checks, so you can access the memory. And the other feature of this is that they use remote attestation to ensure that the CPU and enclave has the right platform and it has the right integrity. So a remote user can trust that it's communicating to a cloud computer that has the right CPU and the right enclave. One of the things about this technology is the OS is still managing the availability of the resources, even though the OS can't access the memory. One thing the OS can do that people shown in the past is that a malicious operating system can interrupt the enclave frequently and also control the execution of the enclave at instruction level granularity. There's this tool, one of the researchers in the community, Jo Van Balk, has developed, SGX step, that enable you to basically control the execution of enclave with single stepping. So the idea is that we can attack this with combining GDS with SGX step. The idea is that we execute the enclave until a software register that we want to target have some secrets. Imagine you know the binary layout of a program, and you know at this stage it's going to have a secret that you want to steal. Then when we reach there, we're going to repeatedly cause context switch to the Intel SGX, and then this context switch happen always with the same register state. And as I mentioned earlier, there are these register restore operations that are going to leak data to the gather data sampling. So every time we do a context switch, we can execute the gather data sampling and leak the target register that we want to steal some secret from it. What did we do with this attack? In the paper I published, the idea is that we can steal the remote attestation key or the sealing key of SGX and essentially compromise all SGX enclaves and the security of SGX enclaves. The idea is that Intel SGX remote attestation protocol use some provisioning enclave that is deployed as part of SGX software development kit. And this provisioning enclave seal the attestation key using SGX itself. So if we steal this sealing key, we can also steal the attestation key, and all of a sudden, all SGX enclaves cannot be trusted anymore. So I looked at the SGX sealing function binary. This function essentially called these other functions SGX get key, which is getting a key from the hardware. It's a hardware-derived key. And then that hardware-derived key is passed through this AES key expansion. And when we look at this key expansion function, at the first 3 instructions, the second instruction load the master key to the XMM0 register here. So to attack this, we're going to use the SGX step tool to bring the computation until this next instruction. And here, we know that the XMM0 is going to have the master key, master sealing key. And then we mark this code page as non-executable. So when the CPU go execute that next instruction, it's going to hit an exception. And then we use the gather data sampling to sample data from that register file that holds that register. And then we handle the exception. And we go back, we again face an exception. And we keep doing that until we know that we have leaked all the bytes of that master key. And that way, we can compromise the SGX attestation. All right, so what can we do about this attack? So one of the common way to generally mitigate this kind of attacks against shared microarchitectural buffers is to flush microarchitectural buffers using some mechanism. So right now, there is no instruction sequence to flush the vector register file. And there has not been any indication that Intel is planning to make such an instruction available to the software. It's possible probably to flush the register file with writing some sort of software sequence, let's say when you do context switching. But I highly do not recommend that, because when I tried this, it was not very efficient, but also very unreliable, because the CPU does some optimization inside that there is a chance that this would not be a very effective mitigation. Also, flushing microarchitectural buffers generally does not mitigate attack when there is a hyper-threading situation where two threads running on the CPU core at the same time. The option that is available, the practical mitigation today, is to apply Intel microcode update. And this microcode update prevents the gather from speculatively forwarding data to the following instruction, which it comes with a cost of performance for workloads that use this instruction to access data fast. And the performance, apparently, according to Intel, for some workload could be none, for some workload could be up to 50%, depending if they use this gather instruction and depending if it's on the critical path. Another important thing for mitigation is that people who use Intel SGX need to make sure that they check the remote attestation is correctly, because Intel is going to revoke the old keys and recover the trusted computing base. Because every time there is a vulnerability like this, all Intel SGX are going to be compromised, and you have to, again, recover the trusted computing base. Another important note here is that Intel CPUs, Intel performance cores starting 12 generations are not affected by this vulnerability. I don't think this has been a choice in terms of security. This has been just an accident of some design. But another important thing is if you update your CPU, it's not vulnerable to this particular vulnerability. I mentioned that Intel SGX users need to check the remote attestation. Unfortunately, this is not going to help until September 19. Apparently, all SGX users are going to be vulnerable until then, until the TCB is recovered. So getting back to this timeline, from 2022 to 2023, it was silent. We didn't hear anything about these attacks. So again, we have them again. There is the downfall attack that leaked data from the vector register file. And we have now mitigations that applies to all CPUs until the 11th generation. And these CPUs are used everywhere in the cloud, in the desktop, in laptops, and everywhere. In conclusion, we see that a single hardware vulnerabilities can undermine all security boundaries, including user and kernel, cross-process and cross-VM, and also Intel SGX enclave. We see that downfall attacks are practical and easy to exploit, as I demonstrated by the attack on AES. Also, we see that despite all efforts post the meltdown attack in the past 5 years, we still have CPUs that expose users' data. And we see that complex optimization in CPUs essentially introduce new vulnerabilities. And there are a lot of gaps in pre-silicon and post-silicon validation for testing CPUs and how we test CPUs for security. So I would encourage people to ask their OEMs and providers to provide microcode fixes for this vulnerability. And I have one other demo here now that we have time. And the idea is that This is an attack that doesn't even need to explicitly run on the same CPU core, but the attacker can just spawn some CPU threads and spy on all the texts that are running in the computer system. With that, I would like to conclude my talk. Downfall, exploit the physical register file, and you can learn more about it in the website. There is proof of concept, there is a Q&A, and some other information. Thank you.